break down your max flow into ST paths and cycle?
Yes, perfect. So flow decomposition is a powerful first step in understanding flows. We're going to use it a lot. So the main takeaway was that we could actually use flow decomposition to decompose any flow into ST paths and cycles. Now, in fact, not only could we decompose any ST flow into ST paths and cycles, but how many of these, you can think of these as like the elementary building blocks of flows. These are things that actually carry flow from S to T, and these are things that do nothing and just cycle flow around while meeting conservation constraints. But if we started off with any flow, and we had a graph on n nodes and n edges, how many of these elementary building blocks did we need in this decomposition? Yep. M, exactly. At most M. Because each time we pulled off either an ST path or a cycle, we actually pushed the flow along some edge down to 0. So sometimes you even need the stronger version of flow decomposition to really say that it's important that you can decompose into not too many such objects. And eventually what we used this to do was we used flow decomposition and the notion of a residual to prove min cut equals max flow. So today we're going to take a deeper look at the max flow problem, and then we're going to move on beyond that even more complex problems, namely the min cost matching problem. So today what we're going to be covering is an algorithm called capacity scaling, which is going to alleviate some of the issues of just naively applying Ford-Fulkerson. And then we're going to move on to generalizations of max flow, and actually one special case that we'll study first along the way is what's called min cost matching. So for the second half of the lecture, we're going to cover things like that, and we'll continue with min cost flow in the next lecture. So that's really the game plan for this week. So let me start off with a quick review. One of the main takeaways that you should have gotten from last time was just, first of all, what flow decomposition is, which we just talked about, but also the Ford-Fulkerson algorithm and how it's underspecified in a very crucial way. So we have this Ford-Fulkerson algorithm, which was nothing more than we just repeat the following while there is some ST path, let's call it W, in H, where H is now this residual graph that we defined last time. And it has that along this path, each of the edges has capacity strictly greater than 0. Then all we do is we keep finding such paths and we augment along W. And we augment by whatever this bottleneck is, delta H of W. So remember that augment here means one of two things. We talk about augmenting along a path. All edges in this residual graph can either represent edges which are not completely utilized, so they're not saturated. They can represent opportunities to actually push more flow in their natural direction, or they can actually represent edges in this residual that can represent flow going in the opposite direction that we've already decided on. And by actually pushing in that direction, what we're doing is we're undoing some flow that we already have. So augment here actually means, one of two things: either push more flow along an edge in this path, or if the edge actually came as a backwards edge from something in the original graph, it can actually mean undoing some of the flow that we currently have. And all we do is we update the residual each time we do this, and this is our algorithm, right? So remember that there are actually some pretty important complications now to this algorithm. So let's talk about them. So the main complication here is that we haven't actually decided how we choose which path W, right? So if you remember from last time, something that I sketched but didn't go into that much details on, there was this major issue, which is that if we have that the capacities in the original graph are actually irrational, then what we saw was that actually there are instances where Ford-Fulkerson might never terminate. In fact, it was even worse than this. So when we had capacities were irrational, it was even worse that Ford-Fulkerson didn't terminate. What was actually worse about that example? Can someone remind me? Yep.
It can be arbitrarily far away.
Exactly. So see, there's two things that can happen when something doesn't terminate. You know, one thing could be that it keeps making progress towards the max flow, but it's just taking a smaller and smaller bite each time. But eventually it's convergent to something that is a max flow. But actually what we saw was that there was a more serious issue, is that if you set up the instance right and shows that that's just the wrong way, that you might not only get an instance which doesn't terminate, but in fact what it's converging is strictly bounded away from the max flow, so you never even get close to the thing that you were trying to maximize. So this was the issue, is that it might not even converge to the max flow at all. So you can work through those details, but really what I want to talk about is less of a technicality like this, where we have irrational capacities, but actually an equally serious issue, which is in the same ballpark, which is where capacity scaling is going to save the day. But even in the case where the capacities are themselves integers, and we have some bound on the maximum capacity, let's say they're bounded by some large integer u, well, what did Ford-Fulkerson actually tell us? So how many iterations might Ford-Fulkerson need to actually complete? I heard mu. So u is only the bound on actually, so you could, so u is only the bound on the maximum capacity within the integers. But if we want really a naive bound, I'm not worried about optimizing it right now, then the problem is that the number of iterations, well, in general, it's bounded by the max flow. But what can we say about the max flow? It's certainly at most m, the number of edges, times u, or any other bound that you have on the max flow. So this looks good, except for the fact that u can really be an extremely large integer in a lot of settings. So just to introduce some nomenclature, a lot of times what this is called is, such an algorithm actually is called pseudo-polynomial. So let me tell you what I mean by that. Now it's pseudo-polynomial because it's actually not polynomial in the bit complexity of u. So for things like max flow, you think about actually the number of bits you need to specify the instance of max flow. Well, you certainly need n bits to talk about all of the different vertices. You need m bits to talk about all the different edges. But then when you talk about all of the capacities themselves being bounded as integers between 1 and u, what you really need is you need not u bits, but log u bits. So the fact that this algorithm runs in, has a u factor dependence in it, and is polynomial in the other parameters, might look all right, but that u parameter itself is exponential in the bit complexity needed to define the problem. So in instances where you have wildly different capacities, Ford-Fulkerson just doesn't cut it. Right? So are there any questions about pseudo-polynomial or what I mean here? Make sense? So capacity scaling is going to fix this issue. But I do want to mention one more very powerful corollary to Ford-Fulkerson, which is something that's really immediate from the algorithm, but sometimes we'll use, is that Ford-Fulkerson, something that's important is that it always finds, in this setting where the capacities are themselves integers, well, what it finds is actually an integer value max flow. So this is already a kind of non-trivial statement that's very useful, is that a priori, if I give you an instance of the max flow problem in which all the capacities are integers, it really is a non-trivial statement to know that, well, not only is there a max flow, but there is always a max flow that does so with only integer values along the different edges. So this is something that's actually not going to be true when we move on to more complex types of flow problems like multi-commodity flow. So I want to pay special attention to this. But just to make sure you guys are paying attention, so what about the converse to the statement? So if I take an instance of the max flow problem with capacities that are integers, is every max flow, does it have only integer values? No, right? Don't even need to vote on that, so definitely no. But this direction is true and it's very useful. We're going to talk about it later when we talk about matchings, for example. But for the time being, let me tell you about, this is the main focus of the first part of the lecture, is how do we get rid of this really bad dependence on U and get something that actually depends logarithmically on U instead. Yep.
Is this issue true of like the specific ways of choosing Ford-Fulkerson iterations, or like every possible thing in the Ford-Fulkerson system?
So we're actually we'll give different ways to choose augmenting paths that don't have this issue. In fact, there are many different ways that you can talk about choosing the path. So capacity scaling will give us one way, and it'll have better dependence in terms of U. But there are actually completely different ways to choose paths that have no dependence on U whatsoever. So I'll talk about that after we do capacity scaling, because just like here we have this notion of pseudo-polynomial time, there are many other notions that I'll get to later, things like weakly polynomial time, which is what capacity scaling would give us. And there's even something called strongly polynomial time. So sort of looking more broadly, a lot of these problems, we're going to revisit them when we talk about things like linear programming. And linear programming is actually, one of the great questions in algorithms is, can you devise strongly polynomial time algorithms for it? No one knows, and that would probably win you a lot of money and someone would give you some sort of prize. But in a lot of special cases, things like max flow, we really do have strongly polynomial time algorithms, so I'll tell you a little bit more about that. But before we get ahead of ourselves, let's talk about capacity scaling. So capacity scaling is a pretty simple idea, but powerful. In fact, there are a few different versions of this basic idea. So today we're going to be talking about capacity scaling. And the idea for capacity scaling is pretty simple, is we want to augment along the fattest paths. First. So remember that some of the examples where Ford-Fulkerson really went awry were situations where, for some bizarre reason, you were choosing paths that allowed you to push very little compared to other paths that were out there. So the first basic fix you can think about is, why should you really choose an arbitrary path and choose something that's really pathologically bad for the path you want to augment along? But what if instead you look for the path W, which has the largest possible bottleneck, so it makes the most progress towards getting to a max flow? Now there's actually, what I want to distinguish between is there's something that's actually literally choose the fattest path every time. There's actually a variant which is capacity scaling, which doesn't pick the fattest path, but it does it in different scales. And so that'll give us a little bit of a speed up over the other things. So I really want to describe that because that's a general approach. We're really talking about when you have problems with bit complexity issues, you have large values, treating the most significant bits first. So it's not actually that tailored a technique, just the max flow. So I think it's worth it doing it that way. So in order to define what this is, let me first tell you that we're going to need the notion of what's called a D residual graph. So we have the residual graph from last time. Now the D residual graph is going to be something very simple. It's going to be just the residual graph. But where we prune out, we just delete all the edges So very simple is we just don't worry about these small capacity edges. So d is some integer parameter. And we take our usual residual graph defined on whatever our current flow is. And all we're going to do is we're going to throw out all of the edges which are themselves too small to worry about. So the notion of d residual graph makes sense. Now let's talk about, and let me do it over here so we keep it up throughout the course, so that throughout the lecture today. Let me define what capacity scaling is. So here's the algorithm. What we do is we start off with d equals u. Remember that u is our bound on the largest capacity of any of the capacities of the edges, and it's an integer. And all we're going to do is we're going to keep considering smaller and smaller scales. So we keep doing this as long as d is at least 1. Now what we do is we let hf of d be the d residual graph. So we have some current flow, and we find the residual, and we remove all the small edges. And all we're going to do is in this graph, we're going to do augmenting paths. So we're just going to choose any old ST path, W, in this new D residual graph. And then we're going to augment, align it by as much as we can, at least with respect to this residual graph. So we augment by the bottleneck in this D residual graph we've created. And then we update the residual graph. And lastly, all we do is we set d to be d over 2. So very simple algorithm. Does this make intuitive sense? Right? Just considering smaller and smaller scales and getting as much as we can on the way towards our max flow early on. Okay? So algorithm makes intuitive sense. Now I think one of the things that's useful to do is first, before really diving into the analysis, let's think about what this does on some of our old hard cases from last week. So one of the hard cases, even in the situation where we had integer capacities, was just the following graph. Where we put extremely large capacities on all but one of the edges. And can anyone remind me, what would Ford-Fulkerson do if it, if you really wanted to break it? How would you choose the paths in a way that you make very little progress? Yep.
You would choose the 1 to 2 path, and then when it gets left, you take that again until you take
Exactly. So all you keep doing is you keep thrashing over this edge and each augmenting by about 1 flow each time. But this one edge would always be the bottleneck, and you wouldn't make much progress. So why does capacity scaling completely? Actually, how many steps does capacity scaling take to solve this problem? How many augmentations? 2, right? So from all capacity scaling would do is it would do exactly what we hoped, and it would completely ignore this bottleneck edge. So this is, of course, a pretty contrived example, so of course it should work pretty well here. But it would ignore this edge in the middle entirely, because it's just not at the right scale. It would find one augmenting path, and then it would find the other, and then it would actually finish. It would never find another augmenting path again. Right? So what I want to do for the first part of today's lecture is we just want to analyze capacity scaling. Let me first tell you a theorem about how well it does, and then we're going to prove it. It'll be pretty simple. So the main theorem is the following. It's actually a pretty old theorem. So I'm going to let n denote the number of vertices, and m denote the number of edges. And the important thing here, so this is an old algorithm due to Edmonds and Card. Does anyone know either of these two names? me about one of them?
Oh.
Pick your favorite. I'll tell them who your favorite is. All right, I'll call on someone
I like
else.
carp. Carp.
Carp? Can you tell me anything about carp?
Cool guy, proved a lot of
Yeah, I like
things on graphs.
So Carp is pretty famous for, I mean, is a Turing Award winner, for Carp's list of NP-complete problems. So right as Stephen Cook, proved, and it's really called the Cook-Levin theorem, proved that 3-SAT is NP-hard, Carp showed that it's actually a pretty ubiquitous issue, that he showed all sorts of things like 3-coloring and set covering, all sorts of problems were actually NP-hard. So a lot of times when you make progress on one of those questions, you really say, aha, I made progress on one of Carp's original lists. Anyone tell me about Edmonds? Yep.
We wrote an algorithm for minimum spanning trees on direct graphs.
Yep. And also, he introduced the polynomial time notion that we all know and love. So he had such an insanely complicated algorithm for matching that the only way he could justify something that was like an n-7th algorithm was to say, at least it's not exponential time. So it actually predates a lot of issues like Cook-Levin, but that's Jack Edmonds. Digits I don't personally know as much about, but actually that's the right way to cite this, is because actually these were done independently. But the main result is that actually this basic idea of capacity scaling, or even doing fat as paths, what it does is it computes a maximum flow. So why am I saying it computes a maximum flow? Because unlike things like Ford-Fulkerson, we still do need to make a lemma to say why that particular algorithm, when it concludes, actually does end up with a max flow. But it really does compute a max flow when it terminates. And actually it does so, and it can be implemented. And this really comes from the bounds on the number of iterations, but in O of m squared log u time. So this is an exponentially better dependence on u, right? So that's the main virtue of something like this, is that even something as weak as Ford-Fulkerson is not making that much progress, but capacity scaling is going to make much more progress. And even, that one particular example, it would be something where Ford-Fulkerson could take a very long time, but lo and behold, we get something that's much better. So too, in the general case, you get something that's exponentially better in terms of its dependence on u. So that's what we're going to prove. Let's do it. So it's just going to be a few simple lemmas.
So, are you claiming that when it terminates, it always terminates in that time? Or that it always does that time?
It always terminates in that time, and when it terminates, it finds a max flow.
And this version of the algorithm is fine for integer graphs only, right?
Yes.
This is assuming that particular all the capacities are integers bounded by u. What's that financial scale?
Yes, so that's a great question. Just to reiterate, this theorem only makes sense when the capacities are integer, because after all, it stops once v is less than 1. So it's never going to find a flow whose max flow value is like 3/2 or something. Right? This theorem only makes sense for integer. Yes. Okay, so that's a good question, because u could be 1. And then we would have a really, really good running time algorithm. Too good to be true, because even in the case where all the capacities are 1, this is still a non-trivial problem. So that's why there's the 1 there.
But just to be clear, we will not be so mean on problem sets as to deduct points from someone who misses a one pass and things like that. You can always assume that long.
Yeah, exactly. This is not a big issue, but just for my own sanity, I'm stating it this way so that you don't think we can solve things, interesting things, in O of 0 time. Just to make sure. All right. So let's prove this. So there are some simple lemmas along the way. So the first lemma, which is really pretty immediate, and I'm going to ask you guys to actually fill in the details for these lemmas. This is not too hard. So what I claim is that at termination, f is a max flow. So this algorithm is correct. We're going to worry about the runtime and how many times we can go through the different loops in this algorithm in a minute. But the first thing, just to make sure that we're on the same page, is that at termination, f is a max flow. So it's kind of fun to rely on you guys. So can anyone help me out here? How can we prove this? Yeah.
So consider the iteration of the loop when d is equal to 1.
Yes.
Then that if we already had the max flow, that will give us the max flow.
Perfect. So the idea is just to consider what happens when b is 1, and actually what the graph looks like when we actually finish that loop and we have no more augmenting paths left. Is that the only way that we can have no more augmenting paths is what we actually found was a max flow to begin with. So just to make this, just to spell this out, the idea is that when d equals 1, well then this d residual graph where we've pruned out all of the edges whose capacity is less than d is nothing more than the residual graph to begin with. So in this phase when d equals 1, we're actually not doing anything different. Is we're taking whatever our flow is at the beginning, and we're just continually looking for augmenting paths in here. So when we actually run out of such paths, then it means we've computed a max flow, right? So just to spell this out is that when we finish that loop now, if there are no ST paths in H, then we know that F is a max flow. In fact, the reason we know this was, if you remember at the very end of lecture, we gave these equivalent versions of what it means for a flow to be maximum. So we said that F is a maximum flow is one condition, and that F's value is actually equal to the capacity of some ST cut. But the third condition in there was actually that there are no ST paths in the residual graph. So that equivalent version of it was exactly what we needed right here, and that's the end of our proof, right? Makes sense? All right, so lemma 1's down, pretty simple. So there's actually only one more lemma. So this is correctness, and what remains is actually to prove a bound on the number of iterations. So let me start off first by just introducing some definitions for this algorithm. So we will call this loop number 1. We're going to have different bounds on how many times these different loops can run. And we're going to have loop number 2. And all we need to actually finish this algorithm is we need bounds on how many times loop 2 can run and how many times loop 1 can run. Loop 1 is immediate. The main thing is really what's going on with loop 2. So what I claim, actually, the main lemma, it's a pretty simple lemma too, is that what I claim is when loop number 2 terminates, and it terminates for some d, some value of d. Well, what I claim is that the value of f star, which is our max flow, is bounded by the value of the flow we found so far plus d times n. So we have a guarantee on how much more progress there is to make. This is the key idea behind capacity scaling, is that if you just look at the big capacity edges and find a max flow with respect to them to make sure there's no more augmenting paths left in your residual, then you need some type of bound that's somewhat good enough that you've made most of the progress on your way to getting to F star. Right? This is the workhorse behind why in later rounds of the algorithm, you wouldn't actually have to run too many times because there's not that much more room left to improve the flow you started off with. So it makes sense intuitively? So let's prove this. So the proof proof is just that it's just three lines. So what I claim is the following: is that if we start off with a flow, we have f at termination at the end of loop number 2. Then what I claim is that there is an ST flow in the residual. Now, you should keep in mind the difference between the residual and the d-residual. So what I claim is that if when we terminate at the end of loop 2, we have a flow whose value is this, and the max flow is this quantity, what I claim is that that tells us there is an ST flow in the residual whose value is f star minus f. Okay? So that's the idea. Can anyone tell me why? Give me a justification for this. All right, yeah.
Oh, okay. So when you sort of apply that flow in the residual to the original flow part, there's like the flow that's the difference between the max flow and the original flow.
Yep.
And that's going to be a flow in the residual.
Yes, exactly. Or another way to put it is, well, I mean, my residual is with respect to this flow. So what I can do is I can undo this flow and send all the flow back that way. That costs me this much value because that's how much is now entering S, even though we want flow to leave S. And then you're back to the original graph and you could just send f star the other direction. So that actually gives you an ST flow in the residual whose value is this. Now we're almost done with this because what I claim is we're going to do the same basic idea. We're going to let S be the nodes reachable from the source S in what? In the D residual graph, right? So this is the same basic idea as last time, is that, remember, at the end of termination, we no longer have any more ST paths in the D residual. So if we take the set of nodes that are reachable from the source, then we get an ST cut, right? Because we have some set of nodes that contains the source. And now the only other step, I haven't left myself a lot of room to finish this proof, as you can see. Then what I claim is that if we take that set S, it's going to prove the lemma for us. So the reason is that then, if we take this set capital S, and we look at the capacity of this ST cut in the residual H, which is where our max flow resides, then what I claim is that this is at most D times M. Why? Yep.
Each edge in this residual graph has capacity.
Exactly, right? So all we did was, in the D residual graph, we removed all the edges whose capacity is less than D. And then all we're doing is we're considering the capacity in the actual residual. We don't remove any edges. And what we had was an ST cut with no edges crossing. And we add back in those edges, we add back in at most M of them. And each one has capacity at most D. So now what this means is that we can just appeal to max flow is bounded by min cut, right? See, here we have an ST flow in the residual, whose value is f star minus f. But here we've created a cut whose capacity in H is at most D times M, and that finishes the lemma, right? So max flow here is with respect to H, is itself bounded by the min cut in H, and that finishes the thing because we have f star minus f is at most D times f. So that's the key lemma. Yeah, so you would have a strict inequality here, but absolutely. So this is actually tight here. Are there any other questions? I mean, this is the workhorse behind capacity scaling. So after this, everything will be immediate. Yep.
So the residual graph, I thought you removed anything that was less than D, right?
Yes. So keep in mind, there's two residual graphs here. This is the D residual graph, and this is the residual graph.
Okay, and the
capacity then refers to the residual graph or the d residual?
This refers to the capacity in the residual graph, right? Because the capacity in the d residual graph of that cut would be 0 because I have no ST paths, and that's exactly the set of things that are reachable for us. So it's really going that we have a cut in the d residual graph. We add back in those edges. That can only increase the capacity of that cut by most d times m. But that extra thing is what allows us to push now a flow of f star minus m. So that's the 3-line proof of this algorithm. Yep.
We're not actually using Maxwell cut, we're just saying Maxwell less than.
Yeah. We're not using max flow equals min cut. We're just using the weak duality version where a min cut bounds a max flow. Exactly.
We don't have it. Well, max flow is
Well, it's a cut. It's a cut. Yeah. So this is at most any cut, any ST cut in H, but great question. All right, so now I claim we're done. So let's just put the pieces together and get our algorithm. So let's erase Ford-Fulkerson. We're done with that. All right, so let's put it all together. So what I claim is loop number 2 iterates at most 2m times. So forget about the 2 first when you think about this. I mean, the basic idea is that at the end of the previous iteration, we're off from the max flow by at most an additive b times m. Every time we run through loop 2, we add something noticeable to the flow. How much do we add? Well, this is what was true when we terminated for some value of d. The next time through, we actually have the value d over 2. So every time we augment, we get d over 2. And that's where this extra 2 comes from, is that loop 2 can't iterate that many times without actually exceeding the budget of whatever the max flow is. And loop number 1 is very easy to bound. How many times does loop number 1 run? 1 plus log u. The 1 is important, as we talked about. But the final thing that we need is, what I claim is that the time to compute an ST path, because this is the basic operation that we do inside loop 1 and loop 2 in the residual, or in a D residual, is O of m. So that's the entire proof, right? We get an m times an m, so m squared, times 1 plus log u. Yep?
Could you, in more detail, say why the first one is true?
Why the first one is true?
Yeah.
So this is just building off of lemma 2. Now the point is, think about what happens at the very beginning. Let's put d as u. We know that when we run through this algorithm, at the end of it, we're off by an additive m times u. The next iteration of the loop is actually u over 2. So every time we actually run this augmentation, d, our value is u over 2. So we add u over 2 flow. Because any bottleneck we find, that's the minimum bottleneck that we can find. So that means we can exhaust that at most 2 times m times. It's just because this is the end of the iteration for some value of d, and the next value of the iteration we have d over 2 is how much we boost by.
Why are we augmenting by at least d? Like, why is delta sub h of d at least d?
Because this guy right here, see, we only have a d residual graph, so that means all of the capacities of all of the edges are at least d.
After you update the d residual graph, is it still like, does it have the property of a d residual?
Yeah, because whatever residual you have, I mean, it's still d residual. So you take whatever your flow is.
So when you update the d residual, you throw away that.
Yes, exactly. Was that your question too?
Yeah.
Okay, good. So does this make sense now? Are there any other questions about this? Yep.
And just to be clear, when you're updating the D residual, you could add back things.
Yes, exactly. You could add back things, exactly. But this is literally, you have a new flow, compute the D residual. That's it. Right? There's a flow, the only thing that you need to define it is actually what its value is along each edge. So whatever flow you have, you're storing that. You compute whatever the D residual is from scratch, so that you still have this property when you restart, that each edge has capacity at least D. Yep.
So when you're augmenting along the residual graph, the D residual.
The D residual. While there is an ST path in the D residual. Because otherwise you wouldn't be sure that your minimum bottleneck is at least D. It wouldn't be fact.
Wait, have you ever odd edges? I'm barely reaching some really new edges. Because it would never remove note from some edge that you figure that out. By update, you mean decompute the whole
Yeah.
residual graph. Yeah. No, but that also can mean adding edges.
So it could, and it's not actually so important, what I claim, for the analysis of this algorithm. Just because, you know, all we need is that actually your augmentation is at least D when we find it. Yep.
So maybe I'm not completely clear on what's going on. Does this mean that you take forward and backward edges of size at least D?
Yes.
Okay.
Yes.
I was thinking of the size of the original graph.
No. Forward, exactly. So it's D residual is the residual graph. We prove all edges with capacity less than D. Edges refers to edges in the residual. Good. Any other questions? Yes.
Is the reason that you need to have the recompute D residual within the interlude is because you might create edges greater than
You might create edges less than D. That's even the worst thing, right? Is that then, if you didn't recompute the D residual, you wouldn't be guaranteed that whenever you find an ST path, that it's fat enough that it's at least D, and you can actually make noticeable progress.
But there is another version of Kathy's theorem that doesn't quite use this D residual
Yes,
graph.
exactly.
That does not need to update it.
Yes, so this, yeah, exactly. But we'll get to that in a minute or two.
Ah, awesome.
Yes, I mean, this is the version that, so just focus on this. Everyone on board? Makes sense? You could have proved this amazing theorem of Edmonds and Karp and been famous if you were around in 1972. Yeah? All right. All right, so let's think about what we did right now. So we have an algorithm which is m squared times log u, running time for computing max flow. So exponentially better than the naive implementation of Ford-Fulkerson, where you get this u factor, right? So let me take a step back and actually tell you a little bit about some of the nomenclature. We already introduced the nomenclature of pseudo-polynomial because it wasn't polynomial in actually the bit description complexity of one of the sizes. Well, what we actually gave is we gave something that's called a weakly polynomial polynomial. So what weakly polynomial means is that the running time is polynomial in the description of the problem. So originally we had pseudo-polynomial because the thing that actually comes up in the description length of the problem is log u, not u. And here this is now weakly polynomial because all of the things in the running time are themselves, things that show up. It's a polynomial in the various description length you would need to write down this problem. Now there's something much stronger that you can actually ask for. Well, what else would it be called except for strongly polytime? Now, what would strongly polytime mean in the case of max flow is that what you want is you want an algorithm whose runtime is polynomial, but in the number of values, not their size. Or rather, log of their size. So if you think about it, we have two different contributors to the description length of a max flow problem. We have things like n and m that just describe the number of vertices and the number of edges. But we also have things like log u that tell you how many bits you need per edge to describe whatever its capacity is. So what you want for a strongly polynomial time algorithm is you want something that only depends on m and n in some polynomial way, and u doesn't even show up, let alone logarithmic u. Yeah.
How is that possible? Isn't this the case that running faster than the length of the input?
So you have to be, so the point is that in a strongly polynomial time setting, you assume that additions and subtractions and multiplications are actually unit operations. Yes, exactly. So you just think of it as a formal value in there. So I don't want to get into too much about the semantics of what this means, but you can ask for things where the u doesn't even show up at all. Was there another question in the back? Or was it the same question? Okay, great. So one of the reasons I'm mentioning this is that actually for things like max flow, you know, as we'll see later when we get into the next unit that we cover, this is just a special case of something called linear programming. So, you know, we could just take algorithms, polynomial time algorithms for linear programming, and just use them for max flow and say, clearly max flow can be solved in polytime. But the issue is that for things like linear programming, we only know weakly polynomial, and strongly polynomial is one of the biggest open questions in algorithms, whether that's even possible. But for things like max flow, which are special cases, there really are strongly polynomial time algorithms. And they actually come from just a variance of the ideas that we talked about. So instead of choosing, for example, the fattest path or doing capacity scaling, all you do is you actually choose the shortest augmenting path. When you implement Ford-Fulkerson, and by shortest I mean here just the number of arcs that you need in the residual graph to get from S to T. So actually this is kind of funny because the way that you're choosing the augmenting path, we're just talking about how important it is to choose paths which have large bottlenecks and actually to do something that takes into account the different capacities. But this way of actually getting a strongly polynomial time algorithm completely ignores the capacities in how it chooses the paths. It chooses the graph theoretically shortest path to get from S to T. Now the catch is that these types of things run in a worse polynomial time, but there's no u that actually shows up. So we're not going to prove that, but it's good to know that these types of things are out there, that there are things that run in m squared times n time. This isn't the state of the art for strongly polynomial time for max flow, but I'll just mention this as just a simple variant of these ideas that actually really does get you all the way down to strongly polynomial. Make sense?
It's also due to Edmund's Carpenter as well.
It's also due to Edmund's Carpenter-Dinitz, although the Dinitz paper is a different one. There's also the... Well, they got m times n squared as well.
That's for different outcomes.
Yes, fair enough. All right. So if no one else is going to call me on history of max flow, of course Michael is the main culprit.
N is the number of vertices.
N is the number of vertices. Yeah. So this isn't the state of the art for this, but now you know what's out there. So what I want to tell you about now is I want to start talking about min-cost matching. So we're just going to get to the basics of it, but we're really going to finish it off next time. We finish up with min-cost matching, and we also talk about min-cost flow. So this is a cool generalization that, you know, problems like max flow are a special case of linear programming, but there are many other problems on the way to linear programming, and for each of these successively harder and harder problems, you're going to see the same types of ideas paralleled again and again. So just like there's a notion of how do you prove that your flow is optimal by finding a cut whose capacity shows you can't do any better, so too there are versions of it for even versions that have not just capacities but also costs. And even when you incorporate things like multiple pairs of flows. So, you know, it'll look a little mysterious until we actually get to LPs and see how this really falls out of some of the standard LP duality theory. But for now, what I want to do is I want to focus on a problem called min-cost matching. So let me start off by motivating it. so let's do it. So min-cost matching is really a special case of the following. We're going to study this problem eventually in full generality, which this problem is called min-cost flow. So min-cost flow has all the usual notions from max flow. After all, it's a generalization. So what our input is, it's an instance of max flow. So it has all of the usual notions, like we're given a graph with edges with a special pair of the source and the sink with capacities on all the edges. I'm not going to repeat that. But the extra little bit is that we also have costs. So remember, our capacities are U, and now our costs map each of our arcs to some real value. And I won't assume these are positive or negative, they can be either. And now the goal for this is the following. Among all max ST flows, find the one of minimum cost. Yep.
We assume that the cost scales for this flow. You
Yes.
anticipate the cost
Yes.
regardless of how much place.
Yes, exactly. So the cost now will be the sum over all of the arcs of the flow on the arc times the cost that's associated with it. But great question. So the idea is really simple, is that in a lot of settings, just asking the question, is there a max flow whose value is at least t? Well, you could ask to refine it, because maybe there are many flows of that value. Instead, what you could look for is, among all the flows of that value, which one costs you the least? So it's a very natural generalization of things like max flow. I claim it actually generalizes another problem that you've seen. So if you think about this problem, it's clear min-cost flow generalizes max flow. Can anyone tell me another elementary problem which it's the common generalization of? Yep.
Knapsack problem?
Probably not.
Okay, never mind.
Unless strange things were happening in complexity. But any other wild guesses? Yep.
Shortest path.
That was not such a wild guess. Yes, shortest path. So you should think of this as a common generalization of max flow and shortest path, right? Because if, for example, I have an instance of a graph, which the max flow is 1, and I have only capacity 1 along each edge, then all I'm going to do is I'm actually going to find the shortest path between S and T. So this is a common generalization of the two. Now, what I want to do first, though, is before we really get into the full generality of min-cost flow, I want to talk about a special case of this problem, which is min-cost matching. So let me remind you what a matching is, and then we'll get to adding costs on the edges of the matching. But it's a very natural problem, as you'll see. All right, so this is designed as a reminder, but because I think many of you will have seen this before, but a matching, and I'll define it again in case you actually haven't seen it. So a matching M in a graph, all it is it's a set of edges. Let me show you an example, and then I'll tell you the conditions that we require on it. So for example, the following is a matching. It's a set of edges where every node has, at most, one incident edge. Right? So you think about this as like couples being paired up, but you want monogamous relationships. So only one edge for incident 2. Yep.
Are you assuming it's a bipartite?
So we will be talking about bipartite, but let me define bipartite next. questions about what a matching is? Yep.
Aren't matchings usually a subset of the edges of the graph?
Yeah, so we'll talk about that when we get to the that's the bipartite matching problem. Is you're given a set of edges which are allowable covariance. But thank you for the segue, guys. So in the bipartite matching problem, which we're going to add the extra variant of costs on top of this. So in bipartite matching, of course, all of these things are very important that they be bipartite, otherwise they're much more challenging problems. Actually, that's what Edmund solved with his in the 7th algorithm. But in the bipartite perfect matching problem, well, we're given a bipartite graph with some set of edges, so that's specifying which edges we're allowed to put into our matching. And V here we're thinking of, because it's bipartite, it's the set of two pairs of vertices, A and B. And the constraint is that the edges only go between. So I'll use this as a kind of running example. All right. So the question in bipartite perfect matching, you're given this bipartite graph, so the vertex set is split into two parts, and the only edges, they have exactly one endpoint in A and one endpoint in B. And what you're asking then is there a set M of edges that's a matching and covers all nodes? Right? So that's bipartite perfect matching, just as an example. Of course, there are tons of bipartite matchings in this graph. But just to do an interesting one, we could have something like this, which is a subset of the edges we're given. And every node certainly has at most one adjacent edge, but it has exactly one. Yep.
So the bipartite graph force A and B to be.
Yes, for the perfect matching problem. So the perfect matching problem can only have an answer if A and B are actually the same size. So I'm going to specialize everything we talked about to the case of perfect matchings, just because it's a little easier to digest. But this is the setup for the original bipartite matching problem. So you guys should hopefully all know how to solve this problem. Can anyone tell me how to solve it? Max flow, right? So let me go over what the reduction is, but then we're going to add costs into the picture too. So the usual reduction, of course, bipartite matching is an interesting problem in its own right. The usual reduction is just to a very simple type of graph, which computing a max flow will give us whether or not there's a perfect match. So all we do is we do the following reduction. So we take that graph over there, and what we're going to do is we're going to create a super source node, along with a node for each of these different nodes in A. And we're going to have an arc into each one of them. We're going to do the same thing for B with a super sink node, which has edges into the sink. And now the important thing is that every edge in the original graph is actually going to go to a directed edge from A into B. That's it. So we create this graph where all arcs are unit capacity. So who can tell me the statement about how the max flow in this problem relates to the answer for the bipartite matching problem, just as a review? Yep.
Max flow is the number of pairs.
Yes, exactly. Or just to put it in the language of max flow, so rather perfect matching. So what I claim is there is an ST flow of value n if and only if there is a perfect match that covers everything. So this is actually, yeah. Okay. So this is actually pretty simple to prove because remember at the very beginning when I talked about Ford-Fulkerson, I made this point that actually what Ford-Fulkerson tells you is that when you start off with integer capacities, like you do in this one, that the max flow, actually without loss generality, you can assume that it uses only integer capacities on the edges. So that means that the values on the edges are 0 or 1. So lo and behold, you're actually going to get very simple things which actually look directly like ST paths in the natural way. And you just look at where the edges are, and that will be your matching. So this is the starting point. This is one of the reasons things like max flow have so many applications, is because things like matching and scheduling. You could think, for example, about a problem where you're trying to match buyers to houses. So every buyer has some set of houses that they're okay with, right? And then we're really asking, is there a way to actually clear the market where buyers go to some other house? Every buyer gets a house, every house gets a buyer. Now, of course, the reason I suggestively chose this example of buyers and houses is that not everyone has the same utility for each different house, right? So, I'm not a big fan of like McMansions, so I don't want to go to Florida. So maybe I would have a very different type of utility than someone else would for houses in Florida. So you can add an extra element to this, which is, all right, so we know via max flow whether or not there's a perfect matching of buyers to houses, but maybe among all of the different things which are perfect matchings, let's find the one that maximizes some sort of social utility for how much people actually like the things they're matched with. Right? After all, if we have all of those matchings, why not choose something like that? So that'll be the example that we'll be working up towards. So what I'm going to do is I'm going to tell you what should be the analog of Ford-Fulkerson for solving this problem. We're going to go into more details about how to actually do it next time. But one of the cool things is that when you think about these algorithms, along the way it's going to create prices and for both of the two sides. So it actually has a very nice economic interpretation about how you should actually set the price of houses to clear the market, just as a simple follow along from the algorithm that we're going to be designing anyways. All right, so are there any questions about this problem, about the reduction from max flow to bipartite matching? Because if not, what we're going to do is we're going to talk about if edges have costs now. So we've sort of danced around this issue, but the min cost perfect matching problem is the goal is to find a perfect matching of minimum cost. Right? And of course, we're presupposing that there is a perfect matching, but that's something we already know how to decide with max flow. Everyone on the same page? Any questions about this? Any objections? No? All right. All right. So let's do this. So what I claim is we're going to do a very similar type of idea. We're going to create a residual graph, just as we did before. So here's the way that we're going to handle costs in the picture. Is using the following idea of creating a residual. So let's say we start off with any perfect matching. Let's call it M. So this is the analog of when we talked about things like max flow and Ford-Fulkerson. We started off with not necessarily the best, i.e. maximum ST flow. Started off with any ST flow, maybe even a value 0 that puts 0 on everything. Let me do the analog here, which is we want to start off with a perfect matching, and we want to move towards the best perfect matching. So given some perfect matching, M, well, what we're going to do is we're going to construct a notion of a residual, which makes sense here. So this is a residual, which I'll call H sub M. And it's actually a very natural object. So here's what you're going to do, is you're going to apply the following operations. Every time you have an edge in the original graph, and it's bipartite, so it goes from some A on the A side to some B on the B side. Well, you can do one of two things depending on whether or not it's in your current matching. Let's talk about what it does when it is in your matching. All you're going to do is you're going to create this residual graph H sub M, which has a directed edge from A to B. The original thing was not directed because it just was an undirected graph. But now you're going to create a directed graph, which the cost now of AB is what its original cost was. So very simple, right? Now the trick is what you're going to do with edges, which are in the matching. So if instead you have an edge, which is in the matching instead of out of it, well, what do? You put an edge going in the reverse direction, where the capacity, the cost rather, sorry, is minus the original cost. Can anyone give me any intuition for this type of gadget? So why are we doing this, and why does this map onto things we've seen before? Yep.
I mean, if we undo the edge that we...
Yes, exactly. It's actually the same thing. That's why I called it the residual, is because this edge is already in our matching. That's why we put it in the opposite direction, because we can undo it. And that's the same reason the cost is now negative, because when we undo it, that's actually the thing that we get back. Right? All right, so from here, now, let me tell you the key lemma in all of this. This lemma is what's going to pave the way towards getting algorithms. It's very similar to the lemma that happened with max flow, where you talk about if there's an augmenting path, you can increase the value of flow. And if there isn't, you're done. So the same type of thing is going to happen here, but with costs. So we need an analog of what it means to get a better matching. And if this condition isn't met, there is no better matching. So let me write out the lemma, and then we're going to prove it. And then I'll just tell you a few things about it, but we'll really flesh out how to use it next time. So here's the key lemma. This is the thing standing between you and the end of class. Yep?
Question on the lower right hand side of the board down there.
Yep.
Do we want the costs from A to cost of residual graph from A to B, or so that we can B to A?
Oh, thank you.
They're directed at
Thank you. Yes, thank you. Very good. All right, so the lemma is, let's start with M. So we're going to let M be a perfect matching, as we just discussed. Then what I claim is that this residual graph, H sub M, that we just talked about how to construct, it has a cycle of negative total cost if and only if M is not the min cost perfect matching. That's our analog for if there is a negative cost cycle, we're going to make progress. And if we can't make progress this way, we're done. So this is the analog of augmenting paths. Does the lemma make sense? So one direction's pretty easy. So can anyone tell me how you go about proving the forward direction? That if M is a perfect matching, and it has a cycle in this residual graph, which the total cost summed over those edges in that cycle is negative, why should we be able to make the matching still perfect, but a lower cost perfect matching? Yep.
You take some edges from A to B that cost less than the original cost of the
Exactly. So the idea is that actually if you take whatever this negative cost cycle is and you trace it through, what's going to happen is you're going to have some forward edges along the cycle, which lo and behold are edges that you want to add back into your matching. But you're going to trace out some backward edges, which are things that you now undo that were in your old matching. And eventually you're going to reach back to where you came from, which is really a way to rotate the edges in a matching to get something that's still perfect but has lower cost. So that's the idea, is that what I claim is that augmenting along this cycle C, it gives a new perfect matching. Let's call it M prime. And the key point is that the cost in the original graph of M prime is actually the cost of the old matching plus the cost in this graph of the cycle, which is actually strictly less than the cost of the original matching. So this idea is just because, every time we have a forward edge in the cycle, that's going to be an edge that we add. A backwards edge is something that we subtract. A forward edge is something that we add. And then we subtract something else. So originally we had these two edges in the matching, the things that cross an X. And then what we're doing is we're undoing them to actually rotate them around the cycle so that we instead get these two blue edges. We pick up the forward cost of these edges, but the cost in the resulting residual graph is the negative of these costs. So we have a negative total cost. It means that we're actually making progress and we're reducing the cost of our perfect matching. So that's one direction of this, which is the straightforward one. The other one's not too hard either. It just is a little bit more interesting. Are there any questions about this then? Make sense? Objections? All right. So the other direction here is we're going to let M prime be any perfect matching whose cost is strictly less. So we proved one direction because we started off with if there's a negative cost cycle, we can make our matching better. Now we're going to prove the other direction that if there actually is a better perfect matching, it implies that there is some way to make progress through a negative cost cycle. So we start off with M prime, and we actually let it not necessarily be the optimal perfect matching, the one of min cost. We let it be any perfect matching whose cost is strictly less. Now the key idea in all of this is that if you take M and M prime, and you do what's called the symmetric difference. So what the symmetric difference is, M and M prime are nothing but sets of edges. So the symmetric difference between these two things is nothing more than the edges that are in M or M prime, but not both. So it's kind of like the analog of the XOR operation over the edges. All you pick up are things that are in exactly one of the two matchings, M or M prime. Now the point is that because they're actually perfect matchings, right? You can think about this as two simple examples of perfect matchings. If you have two vertices here and two vertices here, then you could have these blue edges representing a perfect matching, or you could have these crisscrossing edges representing a perfect matching. It turns out, and you should check this and think through it yourself, but the idea is that if you take the symmetric difference of two matchings, and they're both perfect matchings, the only thing that you can do is the resulting edges here are actually node disjoint set of cycles. Exactly like they look like in the special case, when you take the symmetric difference of these two perfect matchings, we get this 4 cycle right here that goes all the way around. But you should check that when you're taking the symmetric difference of two matchings, if you think about a node, well, that node is matched in both M and M prime. If it were the same edge in both M and M prime, it would be completely isolated from everything else that's going on in that edge would annihilate. If there were different edges, then it would have degree exactly 2 in the resulting symmetric difference. And you could just keep chasing around these degree 2 nodes until you get back to where you started from. That's why it's actually a node disjoint set of cycles. And now we're actually almost done. So let me tell you why we're almost done. So we have this lemma, right, which we want to finish the proof of. So the idea then is that whatever this set of cycles are, so if we take the cost in this residual graph of, well, the sum of the cost of these different cycles, all the way up to the kth cycle, then all that is it's the cost of m prime minus the cost of the original matching. So this, in the case of just a single cycle, was exactly the thing that we used above, was that these cycles give us a way to slowly go from m to m prime. Now the cycle, actually the cost of the cycle tells us how much the net changes for each operation. So if we know that the overall cost is negative here, because this cost is smaller than this, then what that tells us is that one of those elementary operations of actually changing along a cycle is actually going to be a negative cost cycle, which actually makes progress by itself. So at the end of the day, all this tells us is that hence, at least one cycle must have negative total cost. And that's the end of the lemma. Right? So what can we try and do now once we have this lemma in hand? So let's channel our knowledge from Ford-Fulkerson. If this is our way of actually making progress, what's the most naive algorithm you can think of for actually trying to compute a min-cost flow? I guarantee you it'll be on my notebook. Yep?
Time matching, usually find cycles.
Exactly, right? That's it. So that's actually what the algorithm would be. Now it has a fancy name. It's called Klein's cycle canceling algorithm. And it's exactly what you said, even in the more general case of a max flow. All you do is you find a max ST flow. This lemma has a direct analog when you talk about max ST flows. And all you do is, while there is a negative cost cycle, C, all you do is you augment along the cycle, C. So you should really think about this as actually being, and you do it by the bottleneck again, whatever that minimum bottleneck is. But the important thing is that you should really think of this as morally being the analog of Ford-Fulkerson. Imagine you started off with your ST graph, and instead I create some arc going back from T to S, where the cost is minus infinity, and the capacity is plus infinity. So maybe I content myself, this is why I'm saying it's a moral analog, with just having a 0 total flow. Well then if I added back in this, every time I have an augmenting path in the original graph, I would want to take it, because I could complete it with this cycle. So it's actually doing the analog of Ford-Fulkerson, which it's just looking for any augmenting path, which makes progress. Now the challenge is that you can try and fix this the same way you do with Ford-Fulkerson. How would you try and fix this? You could look for small cycles. One other thing that you could do is you could look for the negative cost cycle, which is the most negative. Actually, the problem is that that's NP hard. So things become a lot more interesting for this because variants of this problem actually become hard to implement. So the question of how you don't run into the same bottlenecks as Ford-Fulkerson becomes much more exacerbated for this. So what we're going to do is we're actually going to use this lemma next time to give an algorithm for min-cost perfect matching, which is going to use prices, and it'll have a nice economic interpretation. And then I'll tell you how you can actually implement something like this for a correct choice of which negative cost cycle called the Goldberg-Tarjan algorithm to actually get it. Yeah.
So this thing works for arbitrary.
Yes. All right. So until next time, I'll take questions offline since we're